Okay, so we return to this problem, and I will answer your question in a moment just now. So, the problem that we are looking at here is that we have two sequential circuits, okay, and we want to check whether they are equivalent or not, and by definition the equivalence is that the output should match for every input sequence. There is another thing also is that the output should match corresponding to every input sequence when the two state machines are in their initial states, right, from there on. Now, you remember that when we talked about product computation, we said that how do you define the product of this? The set of states of the product is the cross product of the states of the individual machines. So, a global state is composed by taking one state from here and one state from here, right. So, concatenate the states of the two machines M1 and M2 and you get the global state. So, if there are m states here and n states here, what is the total number of global states? M into n, right. Now, we said that the output function is defined like this, that if in a state the outputs match corresponding to all the inputs, then the output of the product machine is 1, and if they do not match, then the output of the product machine is 0, right. And then we said that okay, if you see that the output is 0, then the two machines are not equivalent, right. Now, that is not really the case. The case is that whether a state, global state where the outputs do not match is reachable. See, they will always exist, because you can take every pair of states, one from M1, one from M2, forms a global state, right, and obviously in all states outputs will not match, right. So, the question is that starting from the initial state, can you reach a global state where there is an output mismatch? Then they are not equivalent, okay. But those states where the outputs do not match will be there, they may not be reachable from the start state, okay. That is why it is not so simple as just taking the pairs of states and comparing. You actually have to traverse the state space to find out whether those states are reachable or not. Now, coming to the next question that he asked just now is that why do we need the register correspondence? See, this transition function, see this D1, though it is shown as a single box here, is actually a collection of registers, it is not one register. So, suppose there are 5 registers here, so this is not one line, it is a set of 5 lines, right, that are going from this and feeding into various inputs of the combinational function, right. Now, the values in those 5 lines are not the same, they are different values, but every line here corresponds to some line here if there is a register correspondence, because then this register, if this register and this register are equivalent, then there is a correspondence between that, like we saw in the diagram which I drew here, that there is a correspondence between D1 and R2 and D2 and R1, right. That is why I am tying up these two and I am tying up these two, right. Now, once you have done the tying up part between the corresponding registers, you can treat these as independent inputs, right, and then check for combinational equivalence. Now, note one thing, that if you find that these are equivalent, then you have actually shown that they are really equivalent, the two sequential circuits are equivalent, because for every possible valuation that you can give as the output of the registers, the next state and the output matches, right. Now, if they are not equivalent, then can you say that the sequential circuits are actually not equivalent? May not be, because of that reachability issue. Why? Because for the combination of S1 and S2 for which it does not match may be a combination which is not reachable from the start states. So, the two sequential circuits are still equivalent in terms of the outputs that they produce when presented with similar input sequences from their starting state. They may still, that may still hold, but in this analysis we are not able to establish that, right. So, when we say they are equivalent, they are equivalent. When we say that we are not being able to establish equivalence, they may or may not be equivalent, right. But in practice, when synthesis tools try to optimize circuits, they preserve the kind of equivalence that we are trying to check. So, we do not need normally to look at reachability based analysis, okay. But still we should know how they work. So, let us go through the steps. So, if we know that some register correspondence exists, then these are the two steps in the equivalence checking problem. Step 1 is the register correspondence is either guessed using simple heuristics or computed exactly. Step 2 is the functional comparison, where we actually compare the Boolean functions corresponding to the output function and the next state function, right. And this step can be done using a variety of methods including BDD, SAT, ATPG, etc. Now, how do we do register correspondence? So, in many practical design flows, a candidate register correspondence is derived from naming convention. So, typically when the synthesis tool works, it preserves the names of the registers. So, from the names of the registers you know which one corresponds to that. That is the simplest and most common way of doing register correspondence. Otherwise, if that is not given, then a register correspondence can be computed automatically as a greatest fixed point, as we explained below. So, what we do is, so what is the problem there? We have a set of registers and we want to figure out that which registers corresponds to, which registers are corresponding to which registers, right. So, we start by putting all of them into one bucket, okay. This is a very generic algorithm for partition refinement based on a given relation, okay, and we will use it in at least 3 or 4 different places from here on. So, let us understand how it works. So, we put all the registers in one bucket, and during each iteration a unique variable is introduced for the outputs of all registers of each bucket, okay. So, what am I saying? I am saying that take a set of registers, if they are in the same bucket, then the outputs of all those registers are tied up, okay. Just like we did here, we had this, we knew that D1 is equivalent to R2 and D2 is equivalent to R1, so we tied them up, okay. Suppose we did not know this, then all 4 of them will be in the same bucket, right. So, we would have tied up all of them. So, we would have had only one S which is feeding into A, B, X, Y. Is that clear? So, we start by tying up the outputs of all registers in one bucket, and where does that line go to? That line goes to those inputs of the combinational logic which was being fed by the outputs of those registers, right. So, all those inputs are tied up now, right. The next state functions are computed based on these variables. We compute the next state functions based on these variables. If the next state functions do not match for 2 variables, then those two registers are now put in separate buckets, which means that in the next iteration their outputs will not be tied up, they will be independent outputs, right. And in this way, let us see the extreme case when there is no correspondence between any of the registers. What will happen? They will all get split up into individual buckets. So, if there are k registers, I will have k buckets each containing one register, right. On the other hand, if all of them are equivalent, then in the first iteration only we will find that the output functions are the same. See, if there are two registers are equivalent, if you tie up their inputs or their outputs rather, then there is no harm in it. The transition functions will find that they are identical. Let me reiterate. If there are two registers which are equivalent, then their outputs will always be the same. So, we can put them into, we can tie them up, right. So, what are we doing? Initially we are tying up everything and trying to see, does it lead to a contradiction? What is a contradiction? I find that the output, the next state function for two registers are not the same. If they are not the same, then they cannot be the same register, because then if their inputs are not the same, how can they produce the next same value in the next clock cycle? Because registers just receive their inputs and pass it on in the next cycle. So, if their inputs are not the same, then they cannot be producing the same output in the next cycle, right. So, we therefore decide that these two are not in the same bucket, we split them up, right. We continue this until in two subsequent iterations there is no change in the buckets, then we terminate, okay. So, that is a fixed point, right. This is the algorithm. For all buckets I, initially put all registers R into bucket 0, and then in this iteration for all buckets I do the following: initialize output of all registers with variable Vi. So, all registers in bucket I, their outputs becomes Vi, common Vi, okay, which goes into the input of the combinational function. Then for all registers R, compute the next function, next state function delta R based on the inputs V. Is this clear? And then for all buckets, if we find that the next state functions are the same, that means delta R1 is equal to delta R2, okay. For all buckets, for each bucket we take all the registers in the bucket and we find that their next state functions are identical, then we return, then we are done. Otherwise, in some bucket we will find that for some R1 R2 this is not matching, then that bucket will have to be split, okay. Right. Now, what I want you to do is to ponder over this algorithm. What does this algorithm do? This algorithm has a functions, set of functions, those are the next state functions, okay. It has a set of registers. It initially assumes that all registers are equivalent, so it ties up their output, right. So, for the same inputs it checks the next state functions. So, in the first iteration what is happening? For the next state function, the primary inputs are the same because that is I, here I, and the state bits are all the same because these two are tied up, these two are tied up in the first iteration, and we see whether the outputs are matching or not, in the sense that whether the next state functions are identical or not. If the next state functions are not identical, then there exists some combination of values for S and I for which the outputs are not the same. So, then those those outputs are feeding into two registers, we put those registers in separate buckets, and we continue to do this until we reach the fixed point, that is no new buckets are created in some iteration. What I want you to do is to ponder over this algorithm and prove its correctness, prove that it is going to produce the proper register correspondence if it exists, right? Yes.
Who gives this transition function? How do you calculate this delta?
Transition function is the combinational logic, the logic that is given here.
But that is what we want to check, the equivalent or not. We are not sure if it is correct or not.
Yeah, see, no, see, here is some combination logic. Take one next state function. So, this is say the ns next state I.
The example you gave that do a lot of minimization and stuff in the basic level, and then we check the equivalence.
Yeah.
So, if there is any bug in that process, transition functions will not be the correct ones we expect.
Yeah. If the transition functions don't match,
the register equivalence may not be the ideal one we want.
No, the register equivalence, see what are you trying to do? You are trying to figure out whether you can have some kind of register correspondence for which the next state functions are the same.
Yeah, but due to some mistake in the combination logic, the next state function may be wrongly implemented in one of them.
Yes, then
so we get the wrong register equivalence, suppose.
Yeah, but then if you get the wrong register equivalence, then what is if the output function will either not match. If the output function also matches and the next state function also matches, then your incorrect implementation of the combinational logic has mapped you from one equivalent circuit to another equivalent circuit. So, in terms of the output, they are the same. Do you get my point? See, what is this checking? This is checking that corresponding to the register correspondences that this produces, the next state functions are identical, right. So, if I say that Ri and Rj are equivalent, then we know that they are equivalent with respect to the transition functions that are given here, right. Now, if you find that the output function is also matching, then essentially you have found out another member of the equivalence class, which is also equivalent to the original circuit. See, even if you change the transition function inadvertently, it can still map into another implementation which produces the same output sequence, right. Now, so far what we have talked about is how to arrive at the register correspondence. So, I have given you the algorithm and I have asked you to develop a proof for that algorithm. Okay. Now, next step is that how do we check that equivalence between the functions? How do you do the equivalence checking between functions? So, one option is that you do the equivalence checking between the functions using BDTs, right. So, you take next step, take this delta 1 and delta 2, create a BDD for delta 1, create a BDD for delta 2 and then compare them. The other option is to do this with SAT. And how do we do it with SAT? So, see these two functions, they are actually equivalent. Okay, this function and this function are equivalent. Now, let us see how we do it with SAT. So, we are going to SAT solvers will accept your set of clauses in conjunctive normal form. Okay. And once you produce, what is conjunctive normal form? That you have a set of clauses, each clause is a disjunction of literals, right, and the set of clauses are in conjunction. Okay. So, I will first show that how you can convert the circuit into a set of clauses. So, we take one gate at a time. First, let us consider this gate. So, this gate is what? It is an AND gate with inputs A and B and output Y. So, we can represent that by this set of three clauses. We have A or not Y and B or not Y and not A or not B or Y. Okay. Now, just verify for yourself that this actually is what represents the AND function of A and B. This set of three clauses means that Y is A and B. Similarly, we develop the set of clauses for this gate and which is in this line, and the clauses for this one which is this line, right. Note that we use these intermediate variables x and y. We do not try to represent f only in terms of A and B. If you wanted to represent f only in terms of A and B and that too in CNF, then you will have to do a lot of work. You will have to write this entire function in terms of A and B and then convert that into conjunctive normal form. That is difficult exercise, and you know that transforming any Boolean function into conjunctive normal form is not going to work in polynomial time, right.
Can you explain that how, so in the slide, how y is equal to AB is represented by the three clauses? The first.
No, this is very simple. See, the function that I am writing here is y XNOR A and B. Okay. The function that I am trying to write here is y. So, I have A, B, this is an AND gate, right, this is y. I am trying to tell the SAT solver what is the relation between y, A and B. So, I am telling the SAT solver that y XNOR A and B is always true, right. So, this is what I want to tell it. So, corresponding to this, now I convert this into conjunctive normal form. If I convert this to conjunctive normal form, then I have the clauses A or not Y and B or not Y and not A or not B or Y. This is the standard conversion from this to conjunctive normal form. You can see that for conjunctive normal form, you can see that these are the clauses under which, say when you have A, okay, if you have not A, then not Y must hold, right. So, this says that whenever not A, then not Y must hold. This one says whenever not B, then not Y must hold, okay. And this one says that when you have A and B, then Y must hold. Clear? Yes or no? Huh? So, transforming any function into conjunctive normal form is a standard procedure. What I am trying to say here is that we do not try to express f only in terms of a and b and then convert it into conjunctive normal form. What we are doing here is we are reading off each gate and converting it into the corresponding set of clauses using x, y, etc. as the internal net names, right. So, we do not explicitly convert the whole thing into CNF. Is that clear? Now, similarly for this, the clauses will be A or G and not A or not G for this NOT gate, right. Now, what do we want to establish? We want to establish that f and g are equivalent, right. We want to establish that whenever f is true, g is true, whenever f is false, g is false, right. Now, if that is the case, then the negation of that will be unsatisfiable, in the sense that f1 and g0 and g1 and f0 will be unsatisfiable. So, I take the XOR of f and g. What are the clauses corresponding to the XOR of f and g? A for g and not a for not g. Adding these two clauses means that either f has to be true or g has to be true, but not both, which is XOR. So, we push these two clauses along with these clauses into the SAT solver and then ask, is it satisfiable? If it says it is unsatisfiable, then these two are equivalent, right. Clear? Okay. So, if the set of clauses is satisfiable, then we have a valuation of A and B such that f and g receive conflicting values, otherwise as in this case f and g are equivalent. Now, this is to give you an idea about how you can utilize a SAT solver to do equivalence checking for you. So, what you do is you take each circuit, generate the clauses from that, right, and then finally generate the clauses corresponding to the XOR gate at the output, and then ask whether it is satisfiable or not, okay. And based on the answer you will know whether the two functions are equivalent or not. And it is very simple, as you can see, just traverse the circuit, generate the clauses and ask the SAT solver to prove equivalence. This typically is much more scalable than BDDs, because as you are aware, BDDs they blow up in size. SAT does not blow up in size. Why? Because you see the number of clauses is of the order of the number of gates, right. So, where is the complexity going? The complexity that we were getting by the blow up of the BDD, where is it going? See, the SAT solver internally has to search in the state space of these variables to find out whether a satisfying assignment exists or not, right. But that is done very efficiently, because we have more than 40 years of research that has gone on SAT. So, the SAT solvers can solve millions of clauses in less than a second. So, that is why even though BDDs have become quite popular in recent times, people still prefer to use, and in more recent times SAT has become the dominant form of technology that is used for equivalence checking. Okay. I will just talk about one more problem in equivalence checking before we go into the sequential equivalence checking for combinational sequential circuits. This is the problem of retiming. Okay. Now, what is retiming? So, look at this circuit, these blue things are the registers, okay. This is combinational logic between them. Now, what we could do, what we have here is, see, the clock speed of the sequential circuit is determined by the critical path delay from register to register. Why? Because this part of the circuit must be allowed, must settle down before the next clock comes. So, whenever the inputs here change, we must allow sufficient time for the inputs to propagate through here up to the next registers before your next clock comes, right. Otherwise, some arbitrary value will get latched into the registers. Okay. Now, in a large circuit, what happens is, at the end of your synthesis etc., you may find that you can better distribute this critical path by shifting some of the registers this way, that way, or in other words, shifting the combinational logic across the registers, right. So, for example, instead of putting two registers here, we might say that we put the register here, okay, and instead of putting this register here, we might say that let us put it here, okay. Now, you see, what we have done is, we have redistributed the logic in such a way that now there are only maximum of 2 gate delays between any two registers, right, whereas here we had a 4 gate delays between these two registers. So, the signal propagation time here was of the order of 4 gates, here it is the order of 2 gates between any two registers. This is called retiming, and retiming is something which is done in order to improve the clock speed of the circuit. So, after the entire circuit design has been done, synthesized etc., people try to retime the circuit. So, they try to move the combination logic this way, that way across the registers, so that you get lesser critical path delays. Now, the problem is that once you start doing that, the functionality of the circuit can change. It will change, right, because the next state functions cannot be the same anymore, but we still want them to be output equivalent. We do not want the sequential circuit to produce different outputs under the same input sequence. So, it is an interesting problem to see how you can do equivalence checking of retimed circuits.
We can't do combination equivalence in this case, when the circuit is retimed.
We would love to do it, we would love to continue to do combinational equivalence checking, because we know sequential equivalence checking involves state space traversal, and that is something which we want to avoid as much as possible, right. So, there are some nice techniques for doing this. What is done briefly, I cannot go into the details of this. This is a very new and relatively new and still ongoing research area. So, what is done is that you preserve the retime logic from synthesis flow and apply it to make both designs compatible. So, what you do is, you take the original circuit, you take the retimed circuit. What has the retimed circuit done? It has moved some of the combination logic across the flops to the other side, right. Now, the combination logics are not identical anymore, right. So, what you do is, you take the patch, the logic that was patched out of from this side, and put it also on the other original circuit, and then do the equivalence checking, all right. So, what you do is, you change the modified circuit a little bit, you patch the original circuit a little bit, and then check the equivalence between the two. I can give you references on that from where you can read more details, but going into the details of how you do that patching is beyond the scope of this course, but I can give you literature on that, but this is a very interesting topic. I mean, how you still manage to map it back into combinational equivalence checking and then use the standard equivalence checking tools, right. Now, the thing that we have left out so far is the sequential equivalence checking when register correspondence cannot be found easily or it does not exist, right. That is the case where we compare state machines. Now, remember that the states, the state machine as such has several things. I mean, the number of flops that you need is depends also on the state encoding, right. It depends on the state encoding, the combinational logic depends on the state encoding, okay, and whether you have minimized it or not. So, what we are going to do is we are going to look at a very fundamental algorithm which has been developed ages ago, before the advent of VLSI or anything, which takes a relation and a state machine and partitions the state space based on that relation. Okay. Again, equivalence can be defined in various ways. So, the equivalence function, the function which determines the equivalence between two states, can be defined in many ways, the most popular ones being bisimulation equivalence and stuttering equivalence. I will talk about bisimulation equivalence in this, and stuttering equivalence is something which I will come back to when we talk about CTL model checking. So, we are not going to talk about here right now. So, let us look at an example first. Let us see here in this state machine A and C, A or C is a redundant state. Now, why do we say that it is a redundant state? Now, see, when you are in A, if you receive an input 0, okay, you go to B with an output of 1. When you are in C also, when you get an input 0, you produce an 1 and go to B, right. So, their next states are the same, and if you think of A and C as the same state, then when you get a 1, you essentially stay in the same set. So, like here, right. So, there are two things that we noted here. One is that on the same input the next states are same, and on the same inputs the outputs are same, okay, all right. So, we merge the two. Now, how do we generalize this approach? So, if an input sequence X takes a machine from state Si to Sj, then Sj is said to be the X successor of Si. So, B for example here is a 110 successor of A. Why? Because if I start from A and then if I give 110, so if I give 1 it goes here, if I give another 1 it goes here, if I give 0 it goes here. So, B is a 110 successor of A. In our previous notation, what this means is that delta star A 110 is B.
Can we say that it is 410 successor of A?
410 means?
41110 successor.
Yes. It is also, B is also a 11110 successor of A. In fact, it is also a 1110 successor of A. Two states Si and Sj are distinguishable if there exists at least one finite input sequence which when applied to M causes different output sequences depending on whether Si or Sj is the initial state. Okay. Two states are said to be distinguishable if you have two input sequences such that when you apply those input sequences with Si as the start state or Sj as the start state, they produce some different output somewhere down the line, right. Then they are distinguishable. If there is no finite sequence for which they are distinguishable, then obviously because this is a finite state machine, then there is also no infinite sequence for which they are distinguishable, in which case we mean that if you are in Si or Sj, no matter what input sequences are given, the two will produce the same output sequence. A and B are distinguishable here. For example, consider input sequence 0. So, if you consider the input 0, then A produces 1. On the other hand, when you are in B, if you produce input 0, then the output is 1. Output is 0. So, this is 0, this is 1, so they differ. K distinguishable states, if there is a distinguishing sequence of length k, then Si, Sj are said to be k distinguishable. States that are not k distinguishable are called k equivalent. So, here A and B are 1 distinguishable, A and C are not 2 distinguishable, and hence are 2 equivalent. States Si and Sj are said to be equivalent if for every possible input sequence the same output sequence is produced regardless of whether Si or Sj is the initial state. Okay. So, here A and C are equivalent. So, the state minimization problem is like this: minimize M, the state machine with the fewest states that is equivalent to M. Okay. So, two state machines MI are equivalent if for every state in MI there exists a corresponding equivalent state in MJ and vice versa. So, this is the equivalence between state machines. This is the minimization of a single state machine. They are equivalent problems. What is the minimization procedure? Partition the states of M into subsets such that all states in the same subset are 1 equivalent. Again, you see, this is like that bucketing. Partition states of M into subsets such that all states in the same subset are 2 equivalent, then 3 equivalent, then 4 equivalent, until you reach some case where the partitions do not change anymore. That is where we reach the fixed point, and that is where we terminate. Okay. Let us see an example. So, initially we have all of the states in the same bucket. Then we see that for, let us say, for input 1, what are the outputs that they produce? So, these ones produce output 0, these ones produce output 1. So, what can we do? Partition it like this, right? Partition. Now, these are the 2 buckets. Now, look at this thing. On giving output 1, these states move to states within the same bucket. This state moves to a state within the other bucket. So, this state cannot be equivalent to these, right, because the, remember the definition of the equivalence, the next states should be equivalent. So, here you see this next state and this next state, so far they are equivalent, but they are certainly not equivalent to this one, because we have already put them in 2 separate buckets. So, therefore, this and this cannot be in the, because this state cannot definitely be in this bucket, which is, it is already partitioned out of that bucket. This cannot be in that bucket. So, therefore, we need to partition this one out there. Now, we have 3 buckets. Again, you see we have on producing 0, this one produces a 1 and goes here, all of them produces a 1. but this one has a next state here, this one has a next state here, and this one has a next state here itself. So now what is going to happen? This will become one, this will go into different partition, this will go into a different partition, right? Like this. So there are two types of ways in which we split. One is output split and the other is next state split. Remember that there are two conditions for equivalence of states. One is that they should produce the same outputs on the same input, and the other is that the next states should be the same. So if the next states are in two different classes, then we split them. If the outputs are different, then also we split them. So this is the output split function. So if you find that output of R1 x is not equal to output R2 of x, where R1 and R2 are in the same bucket R, then we must split the bucket R. So how do we split it? Let R1 be all of those states in R whose output is equal to output Rx, okay, and then let R2 be the remaining set of states, and then we split the partitions by removing R from that as a partition and replacing it with two sub partitions R1 and R2. Okay. Similarly, we do, so this is output split. Okay. Similarly, we do next state split, where if the next states are not the same, in other words, if a next state one next state belongs to R dash and the other next state does not belong to R dash, then we split it up based on the next states exactly in the same way, right. So like this goes to this one does not go to this one, so we are going to split this one up like this, right. So this is the algorithm that is used for state minimization, right. Now this is another example. You can go through these slides, they are available. So basically we first do a output split, because you see the output here on these ones produce 0 as the output on input 0, and these ones produce 1 as the output on input 0. So we split it up. Then we do a next state split based on this one, because see these outputs are going to different classes like this. So this one gets split up based on the next state split. Then again there is a next state split here. See, that is because that this one on 0 goes here, this one on 1 goes here. So they are not, why do we put them in different classes? Because the next states of these are going to these, and the next states of these are going into the other partition, right. So we split it up like this, and that is the final breakup. Then we reach a fixed point. There is no other split that you can do. So effectively the minimal bisimilar state machine is this. It is called bisimulation equivalence. This definition of equivalence is called bisimulation equivalence. This is the final minimized state machine. And to check if M1 and M2 are equivalent, you can minimize M1 and call the result N1, minimize M2, call the result N2, and check if the states of N1 can be renamed so that N1 and N2 are identical, right. That is a classical graph isomorphism problem. And what is the complexity of graph isomorphism? Well, graph isomorphism is a very interesting problem. It is it in NP? Is it in NP? What is graph isomorphism? Given two graphs, find out whether they are isomorphic or not. It is in NP because you can guess a mapping and verify whether the relations, the transition relations are the same, right. like you guess the register equivalence and then checking it is easy, right. Now that is there, but whether it is NP complete or in P has been an open question for many decades now. It is one of those big problems which has remained unresolved, right. So, people do not have a polynomial time algorithm for graph isomorphism, and we have not been able to show that it is NP complete. So, one of those problems which can make you famous. Okay, so we conclude this lecture here.